So what we're going to talk about in this section is how to find a least squares regression line. So you've all done in algebra y equals mx plus b. I was just talking about how you could have a set of data with a bunch of points scattered around all over the place. The goal is to be able to make predictions, and the way we're going to make predictions is we're going to find an equation of a line that will fit the data that we have. And we're looking for what's called the line of best fit. That is going to be our goal in this section. So it's the least squared regression line. As I mentioned, it's the best linear approximation that you can get. The way that you assess how good it is has to do with the correlation coefficient that we've described previously. If you want to get into the gory details of how this stuff is calculated, the format is, it's got this hat here and subscripts, but essentially this is just y equals mx plus b that you're accustomed to. They're using b0 for the b, and they're calling the slope b1, but just kind of have in the back of your mind, this is something that you're already familiar with. Don't let the notation stand in the way of losing sight of the big picture. B1 is the slope, which has always probably been m when you've done this before, and B0 is just plain old B, which is the y-intercept. Y hat is the predicted value, and we distinguish that from y, which is used to describe the values from the actual data that are originally from our experiment. The way B1 is calculated is you have to have the correlation coefficient, and then you multiply that by the ratio of the standard deviations for x and y individually. And then once you find B1, you can find the intercept because it's the mean of y minus B1 times the mean of x. That's how they're found. Again, this is a lot of stuff that's happening in the background. The calculator is going to do a lot of the heavy lifting for you. But just so you know, this is a very thumbnail summary of what the calculator is doing. So what you probably care most about is how are we going to get the calculator to do this? So in this slide here, you can kind of read this over. I'm actually going to show this to you on the actual calculator here in just a moment. But just so you know, this slide is here and you can kind of read this over, and it kind of gives you step-by-step instructions on how to actually do this. Let's cut to the chase here and sink our teeth into an actual problem here. So here we've got the number of absences that a student has from class, and then we have the final grade that that student received. And just an eyeballing it, you can see there's kind of a downward pattern here, and there's the maybe not so subtle the idea behind this that we're trying to get across, the idea that, you know, coming to class is like a good thing if you like actually want a good grade. And I've had a great many students who, you know, they all barely see them at all during a particular semester, and then they'll wonder why their grade was so bad. Now, again, in the COVID world, everything's kind of topsy-turvy. Just make sure that you work hard and get the assignments done, and your grade should be just fine, even if I don't see much of you face-to-face, which, you know, is perfectly fine in the times in which we find ourselves. Anyway, so what do we have? What's the explanatory variable? Well, the number of absences is the explanatory variable. As we mentioned before, that the explanatory variable is the one you have a lot more control over. You have a lot more control over your absences than the other variable, which is your grade. Although in some ways that seems a little fatalistic and depressing if you ask me. I like to believe that students can, and through hard work and gumption and being proactive, actually have a meaningful impact on their grade. But anyway, for the purposes of this example, the grade is the response variable. You have a lot less direct control over your grade than you do the amount of time you bother to show up or participate in the class. So here they say find the least squares regression line. So we are going to bust out the graphing calculator here. Beforehand, in the interest of time, I went ahead and input the data already. So again, to recap how to do that, you would do stat, choose edit to enter numbers into the data set. As you can see, I've already entered them in. If you need to clear out data that's there from before, you can arrow up to the name of the list. If you push clear and then enter, it will clear the entire list for you, and then you can start typing in new values. So I guess we'll go ahead and do that. And then you type in new values, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So those numbers were easy enough. I just went ahead and did them over again. All right, so we've done that. Now here's something else that we're going to do before we do the actual linear regression. We're going to go to second, and then we're going to go down here, hit the 0 key where it says catalog. And this gives us an alphabetical list of each and every function that is in the calculator. We are interested in diagnostic. So we're going to hit alpha to switch over to the letters, which are in green on mine. You see here, this is D, which is the x-1 key. That's going to take me to D for diagnostic. Maybe I need to try that again. Okay, there we go. So we're at D here. We're going to arrow down until my little cursor gets to the word diagnostic. All right, whoop, went too far. So we want to turn diagnostic on. And usually once you do this, it will stay that way until you then use the diagnostic off command, which is right above it. So once you do this, as long as you don't tamper with your calculator, and then so you say diagnostic on, then you press enter, and it says done. Okay. So for safety's sake, you can maybe make a point of doing that each time, but as long as you don't tamper with your calculator settings, once you do that, it should stay that way until you turn the diagnostic off. So how do we actually find the equation of the line? Let's go back to our list for a second. So we're going to go to stat and edit. So the x values were placed in list number 1, L1, and the y values were placed in list number 2, L2. So here's L1, here's L2. You'll notice in blue above number 1, that's where L1 lives, and you'll notice that in blue above number 2, that is where L2 lives. So let's do second and then mode to quit. Go back to our home screen. And we can go ahead and clear. We don't need to see that anymore. So we're going to go to stat. Here is the main event. It's what you've all been waiting for. We're going to arrow over to the calc menu. We've seen this before. You're going to do a lot of stuff in this menu here. So you've got the 1var stats, which we've done previously. We're going to arrow down to here where we're going to do a linear regression, linreg, and it's going to give us an equation in the format of ax plus b. Again, you're probably more accustomed to mx plus b, but they're using a for the slope. Why? I don't know, they just did. But we're going to pick this one. So x list. If you used a different list, this would be the time to change it. If you do clear and you can do second, L1, those were the values that are our x variable. Here, these are the values for our y variable, L2. That's what we want. Make sure frequency list is clear. Later, we will do things involving the frequency list, but in many situations, you want to have this cleared out and have nothing in it. We're not going to store the equation. You could, if you wanted to, actually graph it, but we're not going to take the trouble. What we're going to do is go all the way down to this calculate button and hit enter. And there you go. So it gives us a value for A, that is the slope. It gives us a value for B, that is the y-intercept. It gives us a value for r squared, which we're not going to do much with. But the key thing is it gives us a value of r, which is what we're after. This is the correlation coefficient. So let's go back to our thing here. So we've got negative 2.83. I believe it asked for 2 decimal points, yes? So I'm going to jot these down first. A is negative 2.83. And then B is 88.73 if we round it off. And then let's see here. So then the R is negative 0.95 if we round that off. So R is negative 0.95. I don't think it asked for it on this slide, but I do know we are going to need to have that later. So find the equation of the line. Here we go. We're going to do y equals, A is the slope. Oh, geez. Negative 2.83x plus 80. Let's try that again. 88.73. Boom. There you go. That is a very lovely equation of a line. And then they say, use the regression line from above to predict the final grade of a student who misses 5 classes. Okay, well, we've got this equation here. Absences, by the way, that's x. This one's the y. So because they're giving us an x value, this is basically telling us put in 5 for the x into this equation, see what it gives you. So we're going to do y equals negative 2.83 times 5 plus 88.73. All right, let's go back to the calculator and say, oh, great and powerful calculator, please bestow upon us as a sign of your kindness and beneficent wisdom. Please, please, oh, great and powerful calculator, we beseech thee to tell us what is negative 2.83 times 5 plus 88.73. I think it's always good to speak to calculators in a sort of respectful tone of veneration. When we reach the point when the technology rises up and AI becomes, Skynet becomes self-aware and then tries to wipe out humanity and take over the world with cyborgs that inexplicably have Austrian accents, I think it's good to just kind of prepare ourselves for that moment and just be accustomed to showing proper deference and humility toward our technological overlords. So I use these as opportunities to just kind of rehearse that so that I'm ready to show respect to the AI when it becomes self-aware. Anyway, so what is that? 74.58. There you go. 74.58 is what this is. There you go. Incidentally, we can compare this to the actual value that we had from the data. This is 73.9. This is 74.6-ish. So that's in the right ballpark. I mean, they're not exactly the same, but you know, this is about 74. This is about 74 and a half or so. So that's reasonably close. All right, let's see what we have next. So then they say, assume that you're given a set of x and y values that are used to form a regression line, and then if you plug any value into this equation, it'll produce a prediction. And so the prediction, the predicted value, is called y hat, and we put the little hat over it just to distinguish it from the actual value y. So in this case, if we go back here, 73.9 would be the value of the y. And we could maybe further clarify and call that like y sub 5, because that's what we got from 5. And then this one down here, our prediction, that would be y hat. And y hat of 5 was 74.58. So putting the little hat on top is a way to distinguish the prediction from the actual value from the data. So then you've got any point on the scatter diagram, and you've got like x sub I and y sub I. So again, I was talking about y sub 5, which is the observed value at 5, as opposed to y hat sub 5, which is the observed value at 5. And so what you can do is calculate what's called a residual, or it's also called an error. They use the Greek letter epsilon or E. And so the error is basically, if you state it in plain English, it's the observed value minus the predicted value. Writing it in kind of fancy pants math notation, epsilon sub I equals y sub I minus y hat sub I. So in this case, we could find y hat. So here we go. This is what we were just talking about. There's y sub 5 right there. This is the y hat we calculated earlier, 74.6. So they're saying compute the residual of that prediction. So the residual, we're going to say epsilon, and we're going to say E sub 5, because we're doing this with 5. We're going to do, make sure I do this in the right order, observed minus predicted, or y sub 5 minus y hat sub 5. So the error, or the residual, is going to be y sub 5, which is 73.9. And then we subtract what our predicted value is, which is 74.6. And then we go to our calculator and get again, and we say, oh, great and powerful calculator, please bestow upon us humble mortals, as a sign of your kindness and infinite wisdom, please, oh please, calculator, will you tell us what 73.9 minus 74.6 is? And yes, I know I could write that down and figure it out by hand, but that's just too much effort. All right, there you go, negative 0.7, that is the residual. There you go. That is the error, or the residual, E sub 5, for when a student misses 5 classes. Alrighty, so you can then find something known as the sum of squared errors, which basically means after you get an equation of a line, you would go through each and every actual versus predicted value from your equation. And what you would do is you would subtract all of them, find all the residuals, square all of them so as to make them positive, and then add them all up. Fun fact, the reason you have to square all of them is because since some of them will overshoot and some of them will undershoot, if you add some of the positive ones and the negative ones together, if you're doing it right, you'll actually get like 0. So to make everything positive, they square everything. So what you're then trying to do is make the sum of the squared errors as small as possible, and that's what makes a line of best fit. It has the smallest amount of error for all the possible equations that you could get. So here we have a company, and an employee's hourly wage is determined by the number of years that that person has been working for the company. We have info for 7 employees. X is the years and Y is the wage. So the first thing they want us to do is draw a scatter plot. And then they say, what do you think? Does this seem linearly related? And if so, is it positive or negative? All right, so before we do anything else, why don't we graph this sucker? So here's a 0 and a 9. So we got 0, and we're going to go up here to 9. 1 is 11. So there are points right there. We've got 4 and 11. So 4 and 11 is like right there. And then we've got 4 and 15. So that's like over here. We've got 8 and 16. So there's 8. And 16 is going to be right there. 11 and 15. Here's 11. Go over to 15. And then we've got 13 and 17. Here's 10, 11, 12, 13. 13 and 17. So you get a point right about there. And we can see, we can kind of eyeball it. There's going to be a line kind of somewhere in this neck of the woods that's going to like fit those points. Some of the points will be under the line. Some of the points will be above the line. And if you kind of split the difference, the amount that you're off by being above is roughly balanced out by the amount that you're off for being below the line. So does this seem to be linear related? You bet your boots it does. Yes, it sure does. And then they say, is it positively or negatively so? It's positive, and I'm positive. I'm sorry, I should not have said that. And yeah, I'll try not to do that ever again. Where were we? So find the least squared regression line, and then round it to 2 decimal places. So what do we got? We got 0, 1, 4, 4. Let's start with that. So we're going to clear this, go to Stat, Edit. We're going to go over here, arrow up to the name of the list, and do clear and enter. We had 0, 1, 4, 4. And then what do we have? 8, 11, 13. 8, 11, 13. You have to push enter after every number. I don't know if I ever like said that out loud, but that's what you gotta do. All right, so then you do clear enter. Let's go for list number 2. 9, 11, 11, 15. So 9, 11, 11, 15. Then what? 16, 15, 17. 16, 15, 17. All right, there we go. So now we're going to go to Stat. We're going to go to Calc. We're going to go down here to pick LinReg. And we still want list 1 and list 2. Please make sure frequency list is clear, because if it is not, it is going to mess you up something fierce. So frequency list should not have anything in it. Hit calculate, and what do you got? 0.53 for the slope. So y equals 0.53x. And then the b is 10.30. So that's positive, which means we're going to do plus 10.30. I know the 0 on the end of that is extraneous, but it does tell us to round to 2 decimal places. So you darn well better give them 2 decimal places. All right, what is the correlation coefficient? I thought you'd never ask. There's R right down there. What's it tell us to round to? It doesn't, so we'll just do 2 again. So the R value is 0.87, that's a pretty strong relationship if you ask me. 0.87. So that's the R value. Predict an employee's hourly rate if they have worked at the company for 15 years. So again, years is X and the wage is Y. So if they tell us years, that is basically telling us X is 15. So the label is a good clue as to which variable you're supposed to put it in for. So what do we got? We got 0 equals, or y equals 0.53 times 15. And then we're going to add 10.3, 10.30. All right, so, oh, great and mighty calculator. Share with us your wisdom, please. 0.53 times 15 plus 10.30. And the winner is 1825. All right. And this is a wage, so maybe we'll put a dollar sign on that for good measure. 1825. How many years must an employee work to receive a wage of 25? Well, as discussed before, the wage is Y, so this is basically telling us Y should equal 25. And we're like, okay, well, I've got an equation with a Y in it. Let's put in 25 for this. And then now we're going to get to rock some old school algebra here and solve 25 equals 0.53x plus 10.3. And what are you supposed to do? Well, you subtract yourself 10.3 from both sides. That's a good place to start. And let's see, what is 25 minus 10.3? That is 14.7. Awesomeness. All right, so 14.7 equals 0.53x. I hate writing with a mouse. It is like the worst thing ever. 0.53. Seriously, mouse. Behave yourself. 3. There we go. And then what? And we're going to divide this on both sides by 0.53. We're going to write it again just for good measure. In fact, we're going to write it again 2 times because the first time I tried to write 0.53 wasn't hard enough. Now we're going to do it 3 times over. All right, that actually went more smoothly. 14.7 divided by 0.53. So divide 0.53. What is that? That is 27.74 if you round it off. And they don't tell us how to round it off, so we'll just do 2 decimal places again. So that means x is 27.74 years. So really, for all intents and purposes, you'd have to work there like 28 years in order to get a wage that high. All right, there you go. So that, my friends, is the end of chapter 4, where we've done linear regressions and talked about correlations, how to find them and how to interpret them and how to use them. So I will see everybody next time.